All right, welcome to 16.4, Titrations. All right, so a neutralization reaction is a reaction between an acid and a base. Again, these generally happen in an aqueous solution, even though water won't always be present. You're going to see that aqueous listed next to the acid and next to the base. You're always going to produce a salt and water. Those are always going to be the products of a neutralization reaction. Now keep in mind, I know you've heard me say it several dozen times before, but a salt in chemistry is an ionic compound. I know we talk about salt being sodium chloride in English, in everyday speech, but in chemistry, a salt is an ionic compound where you have a cation and an anion. So it doesn't have to be sodium chloride, though it certainly could be if your cation, sodium, came from sodium hydroxide, and your chloride, the anion, came from the acid. So your anion's coming from an acid, cation's coming from the base. Ultimately, neutralization reactions are just double displacement reactions. In fact, you've probably written and balanced some already when we did our unit on writing reactions and balancing reactions and predicting products. So magnesium hydroxide, here's our base, there's our cation, magnesium, reacts with hydrochloric acid to form the salt, magnesium chloride, and water as a liquid. Always make sure you're balancing these equations. That'll be very, very important as we get into titrations. You have to have a balanced chemical equation. So there's that equation, and just as I was saying, make sure you notice how it takes 2 moles of HCl to neutralize 1 mole of magnesium hydroxide because of that 2 after the MgOH. So that allows us to work with stoichiometry. Again, notice the 2 moles of HCl, and that stoichiometry allows us to use titrations to determine the concentration of acidic and basic solutions. So in a titration, you usually have a known volume of an unknown concentration of solution. So I just give you the solution. I say we don't know what the concentration is, but you do know the volume. You have 20 milliliters of this unknown concentration solution. And we're going to mix that with a solution of known concentration. And we can use the solution of known concentration to solve for the concentration of the unknown solution. So as we get started here, make sure you guys review this slide. We have some very important terms. A burette is a very skinny piece of glassware with a nozzle on the end, and it allows for very precise addition of solution. You're generally going to fill the burette with what's called the titrant. The titrant is your solution of known concentration. So again, whatever you put into the burette is your titrant, and that's usually what you know the concentration of. You know the concentration is 1 molar HCl, or you know the concentration is 0.5 molar NaOH. So we add it to the solution of unknown concentration through the burette. Down here at the bottom, we see what's called the stopcock, and that's just a knob that you can turn to turn the drip or the stream of the burette on or off. Always good to practice using that stopcock, perhaps with distilled water, before you put your titrant in and begin the filtration, or the titration, excuse me. The solution of unknown concentration goes into a flask or beaker down below the burette, and we call that the analyte. We usually put a drop or 2 of what we call indicator, we'll discuss that in a minute here, indicator into the analyte so that we can tell when you've reached the end point. You can see the color change and you've reached what we call the end point. All right, so you're measuring how much titrant. Remember, titrant is the material, the substance of known concentration. that you're going to put into the burette. So you have the volume of titrant, you add it to the analyte, and we take measurements of pH as you move through the experiment. So our pH starts off very low. That means our analyte, what we don't know the concentration of, would be an acid, and we're adding our titrant, we're adding base. Our pH is climbing, so it's becoming more and more basic. Because of the nature of pH, you can think about it, a pH of 1 is 10 times more acidic than the pH of 2 and 100 times more acidic than a pH of 3. It moves very slow at first. We don't have a very big change. And that's because you have to add a lot of OH negatives to get that first change, and then all of a sudden you don't have to add very many at all, and then you don't have to add 10, you have to add 10 times fewer and 10 times fewer, and eventually your pH is changing very rapidly, even with small additions of pH. But the equivalence point, at the equivalence point, your concentration of H plus is going to equal your concentration of OH negative. Again, we know the concentration of the titrant, so we could use the volume of titrant that we added to reach the equivalence point, and then we can use stoichiometry and our knowledge that at the equivalence point our H plus is equal to OH negative. We can use that to solve for the concentration of analyte. As I mentioned earlier, an indicator is usually used to indicate the endpoint. Indicators are going to change color. Like we see here, we have a clear solution. Make sure you swirl, that's what this image is indicating. Make sure you swirl, because you might get a very quick color change, but it might just be in that localized area where the titrant was dripping in. So swirl, if the color goes away, you're okay. Right here, notice how we've got a very, very thin color change. That's your end point. As you continue to add titrant, you're going to get a really, really dark pink color, and you've already missed your endpoint at that point. You're beyond the endpoint once it turns that bright color. So just the slightest hint of color is your endpoint. And again, it changes very quickly. You can take a look at that graph because of the nature of how pH works. A small amount of OH negative at first is going to have a big change, but as you reach a higher and higher pH, you have to add more and more OH negative in order to get that change. 10 times more, than 100 times more, than 1,000 times more. So each indicator has its own particular pH or pH ranges at which it changes color. You want to make sure you choose a good indicator. Oftentimes you have to know, are you working with a strong acid, or a strong base, or a weak acid and strong acid, or a strong base, and help to choose a good indicator, because indicators change at different pH ranges, and you want to make sure that your endpoint is the same as your equivalence point. If you do a good job choosing your indicator, your endpoint will be the same as your equivalence point. But a poorly chosen indicator, and you might not have the same endpoint as equivalence point. So here's an example. Phenolphthalein will change colors, probably the indicator they used here, the pink color. So phenolphthalein changes color between the ranges of, looks like about a pH of 8.5 and 10. Methyl orange, on the other hand, will change colors, according to this, between a pH of what looks like, let's see, 1, 2, 3, 4, 4.5, a pH of 4.5, and a pH of 3. If we expect our endpoint to be around 4.5, which of these two indicators would we want to choose? Well, we'll want to make sure we choose methyl orange, because we'll have a color change right around where we expect that endpoint to be. So if you chose phenolphthalein, your endpoint would be up here, and that's not the equivalence point. So make sure you choose the correct indicator, and again, in this case, we'd want to choose methyl orange. It has an endpoint very close to the equivalence point. All right, so it would make sense if our equivalence point were always at a pH of 7. But it's not. Again, that should make sense because your H plus equals your OH negative concentration. But it's not always at 7. When you have a strong acid and a strong base, it would be a pH of 7. But when you have a strong base and a weak acid, the pH is above 7. So we see our equivalence point here. That's above a pH of 7. This would indicate that we have a weak acid and a strong base. And vice versa, if you have a strong acid and a weak base, your equivalence point would be below 7. So here we started off with a weak base. Notice how the pH is close to 10 to start. That's not a very strong base. It's a mild base. And so our pH, if we're using a strong acid, at the equivalence point is going to be below 7. Why is this the case? Well, what if we titrated, so we're pretending to titrate the weak acid, methanoic acid. Here it is, HCOOH. Hopefully we're all able to identify this H as the proton that will come off. It's a polar bond with that oxygen, whereas this H is bonded to the carbon, and that's not a polar bond. So this H is going to come off, but we have a strong base, NaOH. Here's the reaction we'd expect to happen. So here's our salt, and we're forming water. Now NaOH, being a strong base, is not going to form in the reverse direction. This won't happen. Our sodium ion is not going to interact with water to reform sodium hydroxide. Sodium hydroxide is a strong base. This is why it was so important 2 days ago for you to memorize that list of strong acids and strong bases. This will not happen in the opposite direction. We will not recreate sodium hydroxide and thus H plus ions. On the other hand, the weak acid, methanoic acid, will move in the reverse direction. So the ion there will pull a hydrogen ion off of water and reform the methanoic acid. This also forms hydroxide ions, which, guess what, makes our solution basic. So this is what's called salt hydrolysis. The anions, again in this case, sodium formate, that's what we formed. Here's our salt that we formed. So the anion will accept the H plus and go back to the weak acid that it once was. That creates hydroxide ions, which makes the solution basic even though you're at the equivalence point. The sodium, on the other hand, will not accept that OH negative. Doesn't matter how many OH negatives are there, you're working with a strong base, this reaction won't happen. Let's take a look at a titration stoichiometry example problem. So theoretically, they have a volume of 18.28 milliliters of a standard solution of 0.1 molar NaOH, and it neutralized the 25 milliliter solution of methanoic acid. What is the molarity of the methanoic acid? First step, always balance a chemical equation. And it's just like stoichiometry, you're always going to need a balanced chemical equation. Okay, we're looking for molarity, so we'll start off with moles over liters of HCOOH, methanoic acid. Here's our unit by itself, 18.28 milliliters of sodium hydroxide. And that's equal to 25 milliliters of methanoic acid. Now, we haven't quite canceled that unit out, but these two are equal to one another. 18.28 milliliters of base was required to neutralize the 25 milliliters of methanoic acid, so they are equivalent to one another. I know the concentration of my base, 0.1 moles of NaOH per milliliter. So I can cancel out my milliliters of NaOH. There's where that came from. I now need to cancel out moles, because I don't want moles in my final answer. Moles of NaOH, excuse me. Make sure you're labeling your moles. We do want moles of methanoic acid. This is where the stoichiometry comes into play. So we have a balanced chemical equation. It's a 1-to-1 ratio. And this is why it's so important to make sure you balance that chemical equation. You won't always have a 1-to-1 ratio, but we do in this case. So 1 mole of methanoic acid and 1 mole of sodium hydroxide. And finally, we want to convert our milliliters of methanoic acid to liters of methanoic acid. And there's a conversion we've been making since the beginning of the year. Cool. So we cancel out our milliliters of sodium hydroxide. We cancel out our moles of sodium hydroxide. We canceled out our milliliters of methanoic acid. And we were left with moles of methanoic acid over liters of methanoic acid. Voila, that's a molarity. Practice makes perfect. So here's some practice. Homework for tonight, due tomorrow. If you'd like a few more examples, I do have a PowerPoint full of examples posted to Canvas. So if you'd like to take a look, there's 3 or 4 more slides worth of examples. Take a look.